Yeah, we'll have to see. You know.
I don't know, I just think he's going to make us at least do it a couple days.
No, hopefully it won't.
I don't know, we should have done it.
I'm just like moving around. I tend to move. I don't want it to go flying off.
Okay. You're fine.
Once I get going, I won't notice anything anyway.
Marvin's our youngest physics student, as you can tell. He's actually only 30 in this sort of thing. So really, he's
It took you a while.
He thought he saw one. He thought he saw one.
It was great.
That's it. I had no idea. Right.
All right, so welcome to the kickoff of the second day of the SPS Zone 18 meeting. So our speaker this morning is Dr. Josh Mosh from Sac State. Actually, before I give the standard bio, let me just give you an outline of what's going on today. So 9 to 10, this talk. Then from 10-ish to 10, 15-ish, 30-ish, Dr. Bill DeGraffenreid, also from Sac State, is going to talk to you about the SPS Congress, which is taking place in the Bay Area, Silicon Valley area, next year.
November of this year.
November of this year. Next academic year.
Yeah, next academic year.
So stick around for that. Then let me ask you this: are there any students here who are interested to give a talk, poster? So, are you gonna give us a talk?
I have a poster.
You have a poster? Okay, so after Dr. Graffenreid's talk, Soji's going to set up this poster, and if you want to ask questions, but more or less it'll be a little bit of a free time. Then at 12 o'clock, we're going to reconvene over in the Science Museum, which is by the planetarium. Have a pizza lunch from like 12 to 1, and then 1 to 2, 1 to 2 is a planetarium show. So that's going to be exciting. And then from 2 to 3, we come back over here for another lecture, and then
the demos come.
Then demos and some other physics fun.
Yeah.
Okay. So actually, now let me get to the bio. So again, Dr. Josh Moss comes to us from Sac State. He did his undergraduate degree at Hiram College. Then he did his PhD at William & Mary. So we actually had a little chat about that last night because I went to University of Virginia for my PhD, and they're kind of like rivals. But and actually we had sort of a common connection. Actually, Mark Scheer, who was a theorist at William & Mary, and actually I don't know if you remember our speaker Jennifer Clark, who was here. Jessica Clark. Basically, she's also from William & Mary, and we also had a little chat about Mark Scheer. So a very influential professor as far as the grad students go. Anyway, so after William & Mary, he did a 7-year postdoc at Ohio State, and then two-ish years ago, he basically came on as an assistant professor at Sac State, and is actually helping work on CSU NUPAC, which is our high-energy particle physics consortium that sort of encompasses all of the CSU. And I actually want to say a little more about that because Josh is going to tell you a little bit about that. Okay, so without further ado, let's welcome Dr. Josh.
Good morning, everyone.
Good morning.
Let me know if you can't hear me in the back. I'll do my best to project. So I'm going to tell you a bit today about particle physics. I'm bad at titles, so I simply put Atlas, LHC, and CERN, because that's what I'm going to talk about. Not necessarily in that order, but subtitle here is what is particle physics, and really why should you care? And that's the gist of it. Why? What do I do? Why should you care about it? Why should you continue to fund me and what I do with your tax dollars? But who are particle physics? Who am I? You see a lot of things on TV, the Big Bang Theory and all this stuff. Not really a great description of what particle physics are. who particle physicists are. But this is essentially particle physics in their natural habitat. This is a picture of the Atlas control room. Work on the Atlas experiment at CERN. And this is where I spent most of my days. There I am there, hanging out, looking at 4 huge screens just like this, laid out across the wall, all our data coming in. It's, usually I'm sitting at one of these desks as well. I'm not always just lounging around, sitting, looking at screens. Or I'm down in what are called our counting rooms, hooking up fiber optics to all our readout electronics, or down in the detector area. So there's lots of hardware work, analysis work, and all sorts of things. Or most likely also drinking coffee somewhere and talking with people. But what is particle physics? For me, it's all about exploration. I'm a little late to be sailing on ships, discovering new worlds. I like to think of myself as an explorer. There's a couple types of exploration. One is exactly like I described. You go on a ship somewhere, you explore. You go to the moon, you go to Mars, you go to other planets now, because we pretty much discovered most things on our planet. I call this large particle physics.
I really like that. That's cool. Large particle physics.
You go out into the galaxies, go out somewhere else, you go somewhere else. But there's also exploration inward. Essentially go down. And this was done, a couple centuries ago. We categorized matter. We created this fundamental table of elements. We said, okay, what is the world made of? It's made of these individual elements. And we said, okay, this is great. This is a pretty complicated table. There looks like there's some structure there. We can arrange them in this manner. These have similar properties, and these have similar properties, and so forth. So it looks to be elements of structure. Something that may describe these things better. And we found that in the form of atoms. Right? There's electrons, neutrons, protons that can make up all of these individual elements on the periodic table. So you can go from here, from our everyday life, you can say, okay, everything's made up of elements, and then you can go even further and say, okay, everything's made up now of protons and neutrons and electrons. This is the start of the 19th century, pretty much. Sorry, the 20th century. And then we've gone even further inside that. So we've gone one level to the second level, and now we're down to a third level. Inside of protons and neutrons, there's also structure. We found that we can make up not only neutrons and protons, there's things like pions and kaons and all sorts of things called mesons that are, you can make a table of these things with baryons and mesons that have all sorts of different Greek names and whatever creative names they came up with in the 1960s. But all of these have structure, and they make up things. The things that make up these are called quarks, and I'm going to talk a bit about that today. This is the level at which I'm talking about particle physics today. Later on, maybe 100 years from now, maybe there's more out here. But right now, we've gone from our world down to the elements, down to atoms, and then inside of atoms, inside of protons and neutrons, we have these groupings of things. So essentially, what is particle physics? We're looking for the building blocks of the universe. What can you start with, like Legos, and start building up the rest of the world? All right, start with those, end up with the Milky Way galaxy. Tough prospect, but this is the goal. So not only do you need to know how and what, well, really what it's made of, these building blocks, but how do they interact? How can you take one, combine it with another, and give something that makes up a proton? So here is our latest table. This is our periodic table for particle physics. It used to be this square block, now we've rearranged it into a circle. It's very nice and symmetric. And it's broken up into the colors here. And the colors represent different types of particles. So we have the red particles here, which are quarks. These are what we call matter particles. And these have fun names like up, down, charm, strange, bottom here, and top. And I've arranged it this way. Well, strange should be the other way for energy. But these are what are called matter particles. These make up really heavy, fundamental things like protons and neutrons. We also have leptons. These are the green particles here. These are also matter particles, but they are a lot lighter. These are things like electrons, muons, hows. They're essentially heavier versions of one another. The electron is the most fundamental, Although these are all fundamental. A muon is kind of like a heavy electron. There's also things called neutrinos that are flying through the universe. They're created in stars. They come through, there's like a million going through the size of your fingernail every second. You just never feel them. These are the leptons. You also have things in blue here, which are called force carriers, bosons sometimes. These are gluons, photons, W and W and Z. These really deal with interactions, forces, our understanding of how two things interact. These particles make up that circle. And the last thing in the center is the most recent particle found. I'm going to talk a bit about that today. It's the Higgs boson. And it's really a particle unlike any other. And it kind of completes our description of what we like to call the standard model of particle physics. If you're a particle physicist, you just say the standard model. But there's so many standard models depending on what you're doing. But so if I'm going to probably just call it the standard model.
So is that why they did the circle, so they could put the Higgs right in the middle there? I mean,
so I took this off of a documentary I'll talk about later called Particle Fever. And this was the first time I saw it. So it was all about the Higgs. So most likely, yes, but this is picking up speed in terms of the diagram that we use. It's very nice. It's very symmetric.
Right, exactly.
It makes up different circles of what we know about. One thing I haven't mentioned yet is that all of these particles have antiparticles. There's something called antimatter. So for every particle on here, there's also an antiparticle, an anti-up, an anti-charm, an anti-top, and so forth and so forth. And so it's not only these are the fundamental particles, but also their antiparticles. So, but to make up what we see, to make up our universe, you don't need all of them. There's a nice, you can use them all to make things, and we do. We see particles made up of everything on here. But to make up the universe, you really only need electrons, up quarks, down quarks, photons, and neutrinos. Everything else will live for a very short time and decay. Or they're created, live, decay. Created, live, decay. This is all you need to make up the entire universe. And so there's a bunch of things in here that really aren't needed for our everyday world. To go on here with the standard model, we have interactions. How can those things be combined? How can you make up the universe? Well, you need forces, how they interact. And we know 4 at the moment. There's gravity, the weak interaction, electromagnetic interaction, and the strong interaction. And they all have different things they act on, so it's different type of charge. You're familiar, I assume all of you are familiar with electric charge. You've had E and M, and you can see that things that are electrically charged, electromagnetic force acts on. The other forces have charge as well. This is charge is a fundamental quantity or fundamental attribute of particles, like an electron or a proton. So anything that has electric charge, electromagnetic interaction is going to act on. But the other forces have charge as well. Things like color charge, inflation charge. And for gravity, it's really mass charge. Things that have mass will interact via the gravitational force. And you can see which particles experience. All particles experience gravitational forces, or at least all that have mass. Weak interactions, everything, quarks and leptons, anything that's electrically charged. Quarks and gluons. A gluon is a mediator of a strong interaction. What I mean by mediator is all forces can be thought of as the exchange of a particle between two things. Down here is what we have called a Feynman diagram, which tries to explain the interactions. And this is actually a pictorial description of a mathematical function. So we have an electron coming in, an electron coming in, and they are repelled by one another. And they repel by means of an exchange of a particle. In this case, it's the photon. The photon is what we call a mediator of the electromagnetic force. Electromagnetic fields, electric fields, magnetic fields. The mediator of those is the photon. So when we talk about the standard model of particle physics, the things that we understand pretty well, what we talk about is really these things. Gravity is understood very well, but it's not yet included in what we call the standard model.
yeah, when I look at that diagram and I look at the strength of it, I mean, why the hell would we put it in a nutshell? was
In
10
here?
and minus 41, you know? And you look at the other strengths there, you
It's
know?
a small perturbation, small thing down there. We know
I
about
can't
it.
even imagine
Like
it's
to put it
minus
there.
41, right?
No, I mean, if you look at the relative strength, exactly. This is down here at 10 to the minus 41. Electromagnetic 1 strong is 60, so it goes increasing strength over here. And we don't know how to include this. This is really, I'll talk about this later in the talk, but it's one of the open questions. What is this doing here?
I agree.
And how do we deal with this? These, we understand very well at this point. The Standard Model unifies all of these three forces. Essentially, if you look at high enough energy, we can describe these in terms of just one model. These things all fall out. This, I don't know. We don't know what's going on. So I'm going to talk a bit more about the Higgs boson at this point. You've heard, well, 2012 now, we're coming on 4 years since its discovery. The Higgs boson was first called the God particle by Leon Letterman. I really hate this description, but it's caught on, and so we have to deal with it. It's not quite, but it's extremely important for us because it is unique. It attempts to answer a question that has been unanswerable to this point. It's a theory. It was proposed in 1964. This is Peter Higgs. He proposed a theory that incorporated the ideas. Well, theory was proposed, incorporating the ideas of not only Peter Higgs, but Francois Leclerc and a whole bunch of other theorists here. In it, they theorized that if they found this particle, it would help explain why matter has mass. It's kind of an interesting question in itself. I mean, it kind of blows your mind a little bit. Why does something have mass? What is the reason something is more massive than another? Until this point, it's just been a property. It has mass. But why? This Higgs boson and this Higgs field attempts to answer that question. So what's the deal with the Higgs? Well, Higgs boson, for it to exist, there needs to be something called a Higgs field. And the idea for the Higgs field is to explain a very interesting phenomenon that occurs. And there's a difference between this electromagnetic and the weak forces. And it's something called electroweak symmetry breaking. And the Higgs field would explain why the electromagnetic and weak forces kind of separate from one another, why they're not really the same thing. And it endows elementary particles with mass. Why something like an electron has a different mass than a proton. So the Higgs field, like this little comic by PhD Comics, very good site to go check out. They have a nice animation of all of this as well. But it starts essentially as this comic describes. So you have a field that permeates the entire universe. You can't feel it directly, but there are consequences to that field. Every particle is affected by this field, but in different amounts. Essentially, you have particles that are very slowed down by it, and other particles hardly feel it. The ones that feel it greatly have large mass, and the ones that don't feel it very much at all have small mass. You can imagine, say, something traveling through water. Water is the Higgs field. A bullet traveling through water, it's kind of streamlined at least, it can go through much better. It's aerodynamic. It cuts through the water. And the wake that you see from that is a lot smaller. That's a small mass. It travels very fast through the field, through the water. Something that has like a ball. As we try to push it through the water, it's very hard to push it through the water. And it creates a very large disturbance. That disturbance is the mass of the ball. So different things traveling through this field can gain a mass. So in order for this Higgs field to exist, though, one of the predictions is that it needs something to mediate that interaction. And that interaction is the Higgs boson is the mediator of this Higgs field. So in order the Higgs field exists, we should see the Higgs boson. But 1964 it was proposed, never seen. Been searched for. Every particle accelerator for 50 years was searching for this. Never found. But it could be the answer to the question of how do particles gain mass. So in order to find this Higgs field, or to really explore our subatomic world in general, we need something to look at. We need a very large microscope. Right? If you want to see what's going on a little cell. Use a 100 times microscope and you look down and you see what's going on. We need to go down to a very, very small level, 10 to the minus 15 meters. Can't really do that with a microscope. So you can use a large microscope, or you can do something a little cruder. You can just take two things, smash them together, see what comes out, try to reconstruct what's happening. And so for me, this is my very crude particle accelerator. You take two things, you smash them together.
Large particle.
Yeah, very large particle. And so what we would do is you smash two things together, you see what comes out, you look at, you get a muffler coming out. You can't see these things directly, really, but what you see is a muffler come out, you see a tire go this way, you see a piece of glass go that way, and you try to reconstruct what was it that happened at the collision itself. It's a very tough thing to do. You need very precise measurements. So what's going on in a collision? Well, I'm going to stick to proton-proton collisions. There's lots of types of particle colliders, electron-electron, electron-proton. There's pions. But I'm going to stick to protons because that's what we do at CERN at the moment. You have two protons that come in opposite directions. So you have some center of mass here. And you expect to find only what is inside of a proton, right? You collide the cars together. You see a muffler come out. You see a steering wheel. Those things were in the car already, right? But that's not really what happens for proton-proton collisions. Something entirely new can come out. It has to do with, lack of a better term, this quantum magic that happens, right? Where E, the energy, and mass, mc squared, are equivalent. So if you have a lot of energy in your proton-proton collision, that energy can be transformed into massive objects. New things can come out. Mass and energy are interchangeable. So if you have faster protons, you have more energy in this collision. More energy in the collision means you can create more massive things. So you can have, what's my nice analogy Bill gave me at one point, is that you have the two cars come in and all of a sudden you see a 747 come out of your collision. Something completely unexpected. But you never see that 747 usually directly. You see the pieces of the plane.
Yeah.
You see a wing coming out. You see the cockpit. And so essentially what we have is you have a menu of particles that you can create. Things that at least we know of at the moment that have a certain mass. That mass needs a certain amount of energy to create. So if you have more energy, you can create more massive exotic particles. Things that we may have never seen before. And the better the technology gets, the more energy we can put in this collision, the more new things we can find. We can go to a more expensive restaurant. So what we need is a machine to accelerate protons or other things. Protons are nice if you can get a very high energy here. And we need to get to yet unreached energies. You need to get to very, very high energies. So one more thing on collisions is that it's not all about energy. Sometimes it's about rarity. Sometimes we may have already seen things. We may have enough energy to make some new exotic particle, but it's very rare. It only occurs 1 in every, 200 trillion or something like that. So in order to see it, you need to have lots and lots of collisions. So rare events means lots and lots of collisions. If you want to win the Powerball, you got to spend a lot of money to buy a lot of tickets. So for discovery, we not only need high energies, but we want a machine that can produce record numbers of collisions. And a good analogy for this is if you want to look at, say, the night sky, if you want to see some really far away, distant star, you take a very short exposure, just a few collisions in particle physics, let's say. And you see these things that are very bright, things that happen very often. But if you want to find the rare events, then you got to take a really long exposure. And then all of a sudden, you see the Milky Way, you see all sorts of new things you've never seen before. So you need lots and lots of collisions. You need a very long exposure. So you need to run all the time. You have lots and lots and lots of collisions. And this is where the Large Hadron Collider comes in. This is the biggest machine on Earth to date. It's 27 kilometers in circumference. This is CERN's campus here. That's an airport. That's Lake Geneva here. The Alps are over here. So it is laid out throughout the French and Swiss countryside. So this, I have the circle. Yes, there. Not quite a circle, but you see the point. The rest of these circles are support particle accelerators. This is the super proton synchrotron, booster here. And they're all kind of feed into the one big accelerator here, the LHC. Kind of put in perspective how big it is. This is where we're here. This is where the LHC would lay in Fresno. Right? It's a huge, huge accelerator. So you have all of this. So it's just around the outside. It's not throughout the entire center. But you can see where it would be. It would interrupt a lot of homes. Question?
Is that the zoo? Where the top is?
I don't know Fresno.
Down on the left?
Down the left.
The Fresno JP Zoo, down at 7 o'clock.
Oh, here.
Yeah,
You've been to the zoo?
He went to the zoo with his class.
Nice.
It was good reading.
That's good. If we put a particle accelerator, we wouldn't go through the zoo.
Of course not.
All right. So this really is the largest machine in the world. So it's 27-kilometer long track, 17 miles. It's not only it's not through the countryside, it's underneath the countryside, and I'll graph of that.
Is that one in Texas going to be that big?
One in Texas was going to be bigger.
Bigger, huh?
Yeah, it was going to be bigger. And higher energy.
I know.
So
I know.
I wouldn't have traveled so far. It'd been very nice. So this is a picture of the LHC beamline, one of the tunnels. It's going underneath. This is a cutaway of the magnets. This is one of the dipole magnets here, and you have two beam lines, protons circulating one way and the other throughout. And so you have two beams of protons circulating in opposite directions. It's not a continuous stream. It's not like you have a stream of protons and a stream of protons. They're what are called bunches. The way we accelerate them is through electric and magnetic fields, and they naturally group in bunches of protons. So you have a few, 160 billion protons in each bunch, and there are 2,808 bunches in each beam. And then they're traveling nearly the speed of light. I mean, you can increase their velocity very, very tiny fraction at that point. You have to go up in a whole lot of energy to put into it. And they go around very fast. So they're going around the speed of light, over 11,000 times every second. And they're made to collide at 4 points. So at 4 points around the ring, these two are steered across one another, so they come in and hit on just about a head-on collision. So how do you do that? I mean, very briefly, if you've taken intro E&M, you know everything you need to know about accelerating particles. It's a very simple thing. You want to accelerate them, you want to make them go faster, use electric fields. You have a charged particle, a proton, you create an electric field, you give it a force, you accelerate it. If you want to steer it, then you use magnetic fields. So you have QV cross B. So each of these here would be, let's say, each of these red cavities here would be a dipole magnet. They go in, the magnetic field gives them a force pushing inward, so they go around, they bend this way, go around, bend this way, and all the way around. You need a whole set of magnets to do that, and there's a whole lot of magnets in the LHC. Every time, in this little graphic, every time they pass through this blue piece, they get a little kick of energy. They get a little force. And so they increase their speed a little bit. In the LHC, it's a little more complicated than that. They're almost constantly being accelerated. The principles are very straightforward, but the technology behind it isn't. You need superconducting coils. In order to get to high enough energies, you need a really strong magnetic field. How strong? You need to get to 7 TeV, you need 8 Tesla. An 8 Tesla magnet that stretches over 2 meters, about 20 meters. And you need 1,200 of them around the ring. It's an incredible amount of energy needed to run these superconducting coils. And we consume around 120 megawatts of power just at CERN. And that's just to run the LHC. So it's a large machine. So the 4 points around the ring in which we have them collide look like this. We have Atlas, LHCb, Alice, and CMS. I work on the Atlas experiment. But there are 4 here. And And I said it's underground, so here it is throughout the countryside. Here's CERN itself, and it's anywhere from 80 to 100 meters underground because the ground is sloped. You have mountains over here, so you get a little closer to the mountains. You're a little further, further away or a little less. But underneath everyone's home, there's an accelerator running way, way underneath. So, as I said, I work on the Atlas detector. It's a big collaboration. To make these things useful, to make them run really, really well, we need a lot of people. So there's about 3,000 members of Atlas. It's constantly changing. From 177 institutes in 38 countries. It's really an international collaboration. From the US participation, you have at least 700 physicists, engineers, and students from 44 different institutes, that's universities, national labs. A lot of participation. And what you see here is this is the Atlas detector itself. You have these big magnets here, and you have, this is one of the calorimeters. I'll show another picture here, kind of give you a size of the scope. So this is without the calorimeters in the middle part. The proton-proton collision would occur right along this axis here. And you can see one standard size European male standing there in the center. And it's a huge, huge detector. You need all of this in order to see all the particles that come out. These are all magnets. Atlas stands for A toroidal LHC apparatus. We like to fudge it a little bit. But you have each of these magnets runs like this. So you have a magnetic field that's like a donut here. There's another magnetic field in the center. There's a solenoid that runs parallel to this one. Here's another graphic. So here's our standard size European people here. It's 25 meters tall, 44 meters long. What I worked on is just this tiniest detector in the center called the pixel detector. It's essentially a big digital camera. It has 80 million channels. I mean, 80 megapixel. It doesn't sound like a lot now, if it's probably on your iPhone at this point, who knows? But in order to detect particles, it's a whole lot of channels, a whole lot of data you have to read out and store. So we had a lot of celebrity visits, Stephen Hawking, here we have Tom Hanks, Alan Alda, the Muppets were by, and we even have an Angry Birds game, Higgs Boson. So we know we've hit pop culture. So the LHC, Atlas, CMS, they've made it to mainstream. Here's a little animation I like to show of what's going on inside the accelerators themselves. So what you're going to see is basically the path of a proton, a couple of protons really, as they're accelerated around the ring. So protons start at basically a gas bottle. They go around what's called a booster and get up to 1.4 TeV. Doesn't probably mean much to you at the moment. We go around the proton synchrotron, get a little other boost of energy. They go into the SPS, the super proton synchrotron, gets them up into higher energies, and then they enter the LHC, and they go around many, many, many times to get them up to their maximum energy of 6.5 TeV at the moment. And there's our nice LHC. It's not all. I don't know if there's any graffiti down there. We pass through the French and Swiss border, and we go inside here. Here's a proton made up of 3 quarks. The 3 quarks in the center. And they're made to go down the beam pipe, one coming from the other side. Here's the Atlas detector. And they're made to collide right in the center. They collide, a whole bunch of new things come out. They create tracks in our detector. And as they go through the detector, they light up different parts. Not literally, but we read out data. We collect information from them. And we can reconstruct pictures that look like this, of where all the tracks were, and try to reconstruct them. It's a hugely difficult prospect because you have, just look at all the different tracks that come out. And this is a pretty mild collision. This is 1 proton and 1 proton. These days, when we get to the LHC, we're actually going into the order of 25 protons colliding each time they cross, even higher in the future. And so you get a whole lot of things coming out. So you need a very fine detector in order to see the individual tracks. And once you have all that data, you've got to reconstruct it. Because you don't get these nice pictures. This is what's called an event display. This is from CMS of a muon. We now know this is a muon, and this is an electron. And you have all these little things that maybe we're not sure what they are. Maybe they're pions or whatever. You get lots of this junk coming out. And we have to figure out what it is, what its energy is in order to reconstruct what happened in the center. Here's one from the Atlas experiment. This is a Higgs boson decay. So you have two muons, these red lines, an electron, this green one, cross section up here. So if you're looking along the proton-proton beam axis this way, you have an electron coming out, muon, and muon. And it takes a lot of time in order to reconstruct all the individual points into tracks, into information. Because, as I said, these occur every, I don't know if I said this actually, they occur every 25 nanoseconds a collision occurs. If you have 11,000 collisions per second, these collisions occur every 25 nanoseconds. We have a lot of data coming out. Here's another cross section, let's say. You can just see the number of tracks that come out. Collision point is here. If you look, take a slice of the detector, if you look at the tracks coming out. Why do they bend? Well, they bend because they're in a magnetic field and they're charged. And so you have QV cross V, and they start bending. And from that bend, you can get their momentum. You can get their energy based on their radius of curvature. So you can get information out. In order to detect them, we need a complicated detector. So you need, each type of particle leaves some kind of different signature in our detector. So you have, essentially it's layered like an onion. You have small pieces, you have a pixel detector and what's called the silicon tracker in the center. It gives you very fine granularity, individual tracks. You have transition radiation tracker. It's essentially, they give you space points, X, Y, Z of every track that comes out. And then you have things called calorimeters. These stop, will try to at least stop every particle to measure their energy. And each type of particle leaves a distinct signature. So say like a muon. A muon doesn't interact with, well, it interacts, but it doesn't stop very easily. It's very massive and has a lot of energy. So it kind of just plows through everything and leaves the detector. So we see a track that just goes all the way through. For a thing like a proton, it's heavy, but it also has a lot of energy. So it makes a track, goes right through the electromagnetic calorimeter, and then hits the hadronic calorimeter and stops. And so we see something that has a track and then a shower. A neutron has no charge. It's not going to bend, and it's not going to leave any signature in the tracker. So all of a sudden we just see a shower in the hadronic calorimeter. But the point is, you see that each one has a distinct signature. And we can start telling them apart. Okay, this track's a proton, this track's an electron, so forth and so forth. And we really want, in order to get all of this, you need a massive detector. In order to stop a proton in a reasonable distance, you need a few meters of lead. So it gets to be quite a big job, a very heavy detector. And we want full coverage, no holes. Because if you miss something, imagine you have a hole here, you miss some electron or muon that goes out that way, then you can't say for sure that you know everything about the detector. Now, you're never going to be able perfect on that, but you do as well as you possibly can. You want no holes. So let's talk a little bit about searching for the Higgs. So the Higgs is nice because this is very typical of all particle searches. So you have something that you're trying to find, and it may exist, it may not. You don't know. And so you have to look through all the data, search, data mine it, search through everything, and without a shadow of a doubt, find what it is. You have to have, beyond reasonable doubt, what a signature for it and show that it actually exists. So the challenge for something like the Higgs, and really any unknown particle, is that, well, Higgs specifically, is you couldn't predict what mass it's at. For new particles, that's the same as well. You don't necessarily know how much they're going to weigh. And how much mass they have tells us a lot about how they can decay, how they can break up, and what signature they're going to leave in the detector. So we can't predict its mass, so we don't know where to look. It couples very weakly to other things. What I mean by that, it's not produced very often. So it's only produced in one of maybe 10 billion collisions. And so it happens very rarely. We need a lot of collisions in order to find it. And you're only going to detect about 1 in every 100. So even if you do produce one, you have about a 1% chance of actually seeing it in the detector. So how do you find this? Well, even when we detect it, say we detect it, it may not be the only thing that looks that way. So my example here is a Higgs boson decaying to 2 photons. So 2 pieces of light, right? those two pieces of those two photons, their energy has to add up to the energy and the mass of the Higgs boson. But that's not, Higgs boson isn't the only thing that can make two photons. There's a whole lot of other things. So you have to separate the Higgs from everything else. So what you do is you create these histograms. So you count every event. You look for two photons in your detector, two photons, you add up their energy, and you plot it. So there's there's 3,500 events that have two photons with an energy of around 105 GeV. And you do this for every energy. You have some binning as you go through. And you essentially have two predictions. You have one where there's no Higgs boson. If no Higgs boson exists, then you end up with just a decaying curve, this exponential decay along this dotted lines background. Then you say, what happens if the Higgs boson does exist? What do you predict? Well, you predict there should be a little bump where the Higgs boson exists, because at that mass, you're going to have a few more events that decay exactly to two photons with a specific energy. So you'll end up with a little bump, called bump hunting. We essentially do this all the time. We make these plots, we look for things that have huge little peaks in them. Well, huge peaks, huge for us. They're little, but to us they show up very nicely. So we did this. We did this not only in this channel, but in many, many different ways, not just the two photons. There's an animation of building the histogram as we take more data. So it starts in 2011, we're going to go into 2012, and build up this histogram. You get more and more events, and there's nothing, well, now you start to see a hint of something that's coming through. You have this background prediction in blue, and the data shows this little bump right at 125 GeV. That bump is enough to tell us that something is happening, because it deviates from this background prediction by enough. Here, we'll see it again. You build up the data, you have this null prediction here, this zero, no Higgs boson. And then, when you collect enough data, you see that there's enough deviation now from the background to say there's something there. And this bit of evidence, along with the other little bit of evidence from another channel and another bit of evidence and another bit of evidence, really convinces us there's something there. They all show up at the same energy of 125 GeV. So something must be there. And this is very typical of what we do in particle physics. We look for new things. So it took a long time. 1964 to 2012, we finally discovered the Higgs. So this is 48 years later with many, many happy people. No one probably happier than Peter Haze. This is at CERN. This is in Australia when the announcement occurred. I'm sitting somewhere right there when it occurred. And it got a Nobel Prize for the theorists, not the experimentalists, but the theorists. They got the Nobel Prize. They waited a long time for it, so it's well deserved. But this is not the end. There's much, much work to do. There's many things that are still to do. This is not, we have essentially completed our understanding of the Standard Model in that the things that need to exist to explain a lot of the phenomenon are complete. The thing we knew had to be there was something like the Higgs. Something to explain how the electromagnetic and weak forces combine. But that doesn't mean we understand everything. We don't. There's a lot that we don't understand. We don't understand how we start from what we know now and go essentially backwards and understand how things began. This is our picture of essentially starting from the Big Bang, expanding out. You start very hot and dense, and you end up with diffuse and cool. This is our universe today. Back at the beginning, it was very, very hot, very, very dense. And we're somewhere in this region, kind of with our understanding, but we don't know where we are here. At the LHC, we produce very, very hot, dense environment in the collisions, which kind of gives us an idea of the conditions that were occurred at this kind of time relative to the Big Bang. Just a few, 10 to the minus 34 seconds after the Big Bang. We recreate these conditions at the LHC. Every time we go up in energy, we go back in time a little bit more. So the hotter we get, the denser we get, we can recreate the conditions that must have been there closer and closer to the Big Bang. Now, we'll never get there in my lifetime, that's for sure. Who knows if we'll ever get there. But our understanding is somewhere in here. There's also this pattern that this is my favorite thing to look for me, is that we have this pattern. If you look at everyday life, we see flowers, we see chairs, we see us. We go inside of that, we see atoms and molecules and elements, and we go inside of that, we see nucleus, nucleus and electron, and we see protons and neutrons. We start exploring deeper and deeper. We try to figure out what everything is made of. And we're essentially at this level. We see that we have electrons, we have quarks. But I showed you this picture here. Our particle physics elementary table. And then now it looks like there's structure to this. It looks like, well, here are quarks. These have all similar properties, especially these three and these three. They have very similar properties. These and these have very similar properties. Just like all of our tables up here all of our columns in the periodic table, they have very similar properties. Is there another level of substructure? Is there something that makes up quarks and electrons? Some one or two fundamental things. I say these are fundamental, but there's 6, 12 around the outside, plus their antiparticles, that's 24. That's a lot. That's a lot. So is there more substructure to this? Is there more things there? We don't know. Another question we've already talked about is why the forces are so different. We don't know this either. If you go backwards in time, go to higher energies, you go backwards in time to the time where the universe was hot and dense, all the forces kind of merge together. All the phenomena can be explained in terms of one force, the strong, the weak, and the electromagnetic. This is what's called a grand unified theory. But this still doesn't incorporate gravity. Why is gravity so weak? How can we get general relativity, which describes gravity, incorporated into the standard model? How can you have gravity and particle physics coexist together? There's many theories out there, but we're not at a point right now to experimentally verify any of them. So we have a lot of work to do. And there's a lot of other missing pieces. There's dark energy and dark matter. How do we explain the motions of galaxies and pulsars and quasars and everything like this? How do we explain their motion? There has to be something like dark energy and dark matter. The visible matter in the universe only takes up a very small fraction. We don't know what this is. I don't know what it is. People try to explain dark matter and dark energy to me, and I get very confused. Because you don't know what it is. It has to exist. And the next question is, where did all the antimatter go? Right? We said there's particles, antiparticles. Our universe is completely made up of matter, not antimatter. We see up quarks, down quarks. Now we can make antimatter, and it's made in stars, and it's made in collisions out in outer space, cosmic ray collisions, and it's made very fleetingly. It exists for a short time and it goes away. Every theory we have so far says matter and antimatter must have been created in equal quantities when the universe began. Where did all the antimatter go? I have no idea. But the universe is so old that all it may take is a very small asymmetry, one way that antimatter decays that matter doesn't, that would change all of the antimatter into matter. There's a lot of ways for this to occur. None of them have been proven yet. One may be neutrino oscillations. But where did all the antimatter go? This is still very much an open question. What gives these particles mass? Now we think we have a handle on this one. The Higgs boson is exactly what we think it is, and we have a pretty good reason to think so. It's still pretty new. It's only 4 years old, so we have a lot of experimentation to do, a lot of measurements to make. But it doesn't explain why the masses are so different. Why do some particles feel the Higgs field a lot, and why do some of them feel it not at all? Why does the photon not feel it at all, right? The photon doesn't feel the Higgs field because it goes through, zips right through it at the speed of light. Anything that has mass cannot travel at the speed of light. It feels that Higgs field and is slowed down a lot. Why are they so different? No idea. So the ultimate question, what is this, in our lifetime, what is this good for? $1 million question. I have no idea. None. Right? There's considerable lag between the discovery of something fundamental and finding out what it's good for. The electron was discovered. People were like, that's great, fantastic. I have no idea what you'll use it for. Right? 100 years later, we have an entire society built off electronics. Now, I think we may be a little bit further than 100 years away of figuring out what's going on with it, like how to use the Higgs or some new particle we discover, but you never know. Protons and neutrons, when they were discovered, that's a nice, one immediate use was nuclear power and nuclear weapons, which is not always great, right? But there are other uses for those, and those are coming into wide use now. Proton therapy, fighting cancer with protons. There's a lot of nuclear energy. Some people have very strong opinions one way or the other on that as well. But we have these discoveries that were made 100 years ago. We're now kind of coming into their own and saying, these are useful. So what are the things that we're finding now used for? I'll probably never know in my lifetime. But the key is they are, and they probably will be useful. It's just a matter of finding out what those uses are, how we can harness that information. But it doesn't mean that what we're doing at CERN isn't immediately useful. The knowledge may take a while, but we've gained a lot of things along the way. There's a lot of accelerator work like proton therapy for medical research, for, I put proton therapy here. You have PET scans, things like that. We have isotopes that you can use to image and to fight cancers. These are all developed with nuclear and particle physics from the knowledge developed there. And not only the knowledge, but the detector work is going to be useful as well. Before we get there, probably the thing that everybody in here is most grateful for is the World Wide Web. It was discovered, was created at CERN in 1989, Tim Berners-Lee. It was really a way to communicate particle physics, well, a lot of physics information, not even just particle physics information between institutes. And so now this is developed into something a little more useful. These days, we have the Lhc Computing Grid, which all of our data goes to. And it's, this was described as vague but interesting idea in 1989. A little different now. And at this point, it's well over 100 petabytes of data. Right? Petabyte is 1,000 terabytes. So you have a whole lot of data that's coming out of the LHC going to this worldwide grid that uses the internet to analyze the data to allow physicists all over the world to access it. You gain a lot of things in detector research, let's say detectors for medical research. All of these detectors that we use on the Atlas experiment and every particle physics experiment, these pixel detectors, silicon strip detectors, transition radiation detectors, halorimeter, all of this technology is then used in other things, like imaging some part of your body. Right? Here's a gecko in 3D imaging, and pixel scans and metapics, different tomographies and the like. You have electron microscopes and the like. These are all things that have been developed along the way for nuclear, particle, and other physics research. So there's a lot of things that, in order to do what we do, we have to push the technology even further, which is nice. One, it gives us all nice jobs to do. So what do we do in Atlas? What do physicists do? To kind of give you an idea of what I do. These are all things that I have worked on in my time on Atlas. I test hardware, that's different material, diamond. I work on diamond pixel detectors, silicon strip detectors. You need to measure the position and charge and energy of every particle that it produces collisions. All of these things, you have to physically sit down in front of and understand the electronics behind it. You have to understand the theory that's going on underneath to understand if what you're seeing is correct. You have to research new ways of transmitting data, so fiber optics, gigabit speed, electrical lines if possible, but may not always be there. And you have to really have an understanding of computer controls. Everything we do is computer controlled. You sit at a computer, like I showed in the control room, and you're actually turning on and off electronic channels down in the down at the detector level. So there's a lot going on. You have solid state physics, optics, E&M, computer science, nuclear particle physics, and much, much more. So you have to you have to have a pretty broad understanding of what's going on in a lot of different areas of physics. And you have to have good data analysis skills. Everything that comes out is 100 petabytes of data. You have to essentially be a data miner. You have to figure out what's going on. We use a lot of simulation techniques, Monte Carlo techniques. You have to compare simulations to data, look for agreement and disagreement. That's a lot of statistics. So this is, what I'm describing here is not unique to particle physics. It's unique to physics, right? In general, you have to be not only a physicist, you have to be a statistician, you have to be an electronics engineer, you have to be all of this in order to have an understanding of what's going on. Doesn't mean you have to be an expert in it, but it's good to be exposed to it. You can always go to the experts and say, hey, can you help me out? And that's how you get better at all. But you need knowledge of a lot of things, standard models, statistics, computer code. But all of these things that are useful in what I'm describing here are useful in many different fields. So if you are a physics major, which I hope all of you are, your skills that you're developing are useful not only in physics, they're useful in many, many other things. So you are learning how to solve problems. And that skill is useful everywhere. I have a lot of friends, actually, the statistics part, they have left particle physics now because they have gotten lucrative offers from Wall Street in order to model not particle physics simulations, but stock simulations. Because it's essentially, it's very similar. It's statistics, it's modeling, it's simulation. So your skills you're developing are very applicable everywhere. And one slide on plugging what's going on here. So at CSU campuses, we have a lot of things going on in particle physics. So Sacramento State, where I am, it's officially joined the ATLAS collaboration now. We joined Fresno State here as part of our ATLAS group, a California State University ATLAS group, sending at least a dozen students over to CERN this summer to do work. I will be there for that, so if any of you are going, meet me there. We'll have coffee, I'll show you around. This is a group of students in front of the Globe of Innovation, one of the LHC dipoles out there we're showing. But the interest in particle physics is really going up. We have this MUPAC consortium with 16 campuses. There's a particle physics class that is taught by Dr. Gao. Hopefully at some point in my future I'll teach it. I would like to do that. But Fresno State, Sac State, we're both members of ATLAS. There is Dr. Clay at Cal Poly, is a member of ALICE. ALICE is a large ion collider experiment. That one actually works, right? Although I always say ALICE, they always say ALICE. So I think that's to make sure that you don't ATLAS, ALICE, that can be kind of tough there. But there's a lot of good things happening on the CSU campuses. And the interest is only increasing. So there's a lot of good opportunities for students. If you want more information, there's a lot of places to get it. I recommend, one, this documentary, Particle Fever. So here, I highlight there. This is on Netflix right now. And it is essentially a documentary about what I've talked about today, the Higgs Boson, discovery of the Higgs Boson. And I like it especially because it's about the ATLAS experiment. It's not about CMS. Those guys, it was a co-discovery between CMS and ATLAS. And this documentary really focuses on the people in ATLAS. If you want more information other than that, there's plenty of other places to get it. There's this ATLAS Live page, atlas-live.ch. It kind of gives you up-to-date information. Oh, that's the virtual visits here. The ATLAS Live page here. It kind of gives you everything that's going on in ATLAS and the LHC. Atlas.ch, CERN.ch. This PhD comic site for the Higgs Boson is it's a video, it's 10 minutes of your time, it's well worth it.
PhD comics is good anyway.
PhD comics it'll take some time if you sit there and look through every comic for the past 5 to 10 years. You can follow us on Twitter, of course. Everybody has Twitter these days, so ATLAS Experiment and @CERN. So, okay, that's all. Thank you.
We have time for some questions.
Well, with the recent announcement of discovering gravitational waves, does that help combine gravity into the standard model?
Not that I know of. I am not an expert on gravitational waves at all. Essentially, we had a nice talk at Sac State from one of the collaborators on there, and that was mostly new information to me. So I can't speak towards that at all. Really. I mean, I don't think that the discovery tells us anything that hadn't been theorized already. Right? It was a great experimental achievement. But Einstein predicted that 100 years ago, and I don't know if that tells us anything how to incorporate it here in particle physics. I wish it did. It would be very nice. But maybe someone smarter to figure it out.
In getting your temperatures up inside the collider, how close are you getting to the expansion period of the universe?
I'm not sure. It's a very good question. So, like down in here.
Yeah.
So let's see here. So we're kind of in this range. It's going to take us a while to get to this expansion period. Probably not in my lifetime. So I don't know an exact energy. When this is predicted to be, we are at energy densities. At the LHC we're at 13 TeV. And this is probably at least a couple orders of magnitude higher than that.
So you have 3 orders of magnitude of temperature.
So
That's
that's
3 orders of magnitude.
it's got to be way up.
So, yeah.
I hope to reach it in my
Yeah, they do
lifetime,
that.
but probably not.
Yeah, so the computer 3 times the size, so you need to.
Yeah, you probably know this much better than me. It's good to have a theorist in house. Direct all the theory questions.
Computers don't know anything.
We're in the same boat there, that's good.
Any other questions?
So what comes after the Higgs? So there are a lot of things like supersymmetry. Actually, you mentioned the dark energy and dark matter. Dark energy is probably not going to help with.
No.
But people keep suggesting maybe that the LHC might find dark matter for it.
You can go in the archive and find hundreds of papers with predictions on where you might find dark matter at the energies. Right now at the LHC we're at 13 TeV. So anything up to a mass of a TeV or 2 TeV is really within reach of what we find. And there's lots and lots of predictions on what particles might occur around that mass region. But we're looking for all of them. This is the beauty of ATLAS and CMS, is we do what are called general searches. Is that we don't care what theory predicts them. Is that we're looking for, exactly like I showed you in Higgs, we're looking for bumps. And then once we find them, these deviations from the prediction, then we'll try to find theories that match them. So we're kind of doing a general search. Like, we don't know what to expect. There's thousands of predictions on what could occur. Some of it might be dark matter. Some of it might be pentaquarks or something like that has already really been found. But different. There's always more to find out there.
Wait, Alice this summer announced they found a pentagon, right? Which is like a big deal.
It was. Sorry.
Oh, is that still?
Okay, next question. It was definitely Alice, and I'm not sure what they named it or whatever, but they had found.
Alice or
It might have been LHC because I think it was in the form of asymmetric collisions. I think it was LHC. But that's something that had been predicted at Jefferson Lab. Actually, there was announcements at a collider in outside of it's Newport News, Virginia. They said that in early 2000s they found one of these things, but never repeated it, unfortunately. And now they found one. So
It was just in the news that D0 analysis is still going on, and they found a tetraquark.
oh, nice.
Yes.
Did not. Oh no, I did. That was just a couple
It
weeks
just
ago.
came out like 2 weeks
Yeah.
ago. Yeah. So that's kind of cool.
It's good.
Tetra
Four
and
quarks.
Yeah.
So I didn't go into this too much in the talk, but a proton is a 3-quark object. You have 3 quarks, you combine them in such a way that they don't have any color charge. They have a neutral color charge. There's a lot of different ways to do that. You can have 3 quarks combined, you can have 2 quarks combined. And that, for a long time, was like, oh, that's all we have. We found a lot of things with 2 quarks, we found a lot of things with 3 quarks. But there's also other ways to produce these things that are colorless, that are 5 quarks or 4 quarks. So you essentially take a 3-quark object and a 2-quark object and put them together, and And you have a 5-quark object, it's colorless. And you have 2 and 2, you put them together and you have a 4-quark object. But they're much rarer and they're much harder to find, at least where we are now.
Actually, my question was, so you described how the Higgs boson was discovered, but primarily that was because it was kind of in the mass region and we saw a bump where we expected the Higgs to be. I'm curious, since the discovery, what have we learned about the Higgs in terms of properties that are predicted for it? And is there anything that we've discovered so far, or we have hope to discover with more data, that will help us flesh out what kind of Higgs it is?
Mostly so far, it's been, we really nailed down its mass, that's one. Spin is the other. But other than that, there haven't been too many.
Branching ratios?
A little bit of branching ratios. And you have that because we have a different, branching ratio is the percentage of time it decays one way versus another. Higgs decaying to 2 photons versus Higgs decaying to 4 leptons, 2 electrons, 2 muons. And it's essentially your rolling dice. Is you have a Higgs boson, how does it decay? I'm going to roll the dice. This time it decays to 2 photons. This time it decays to 2 electrons, 2 muons.
It's like quantum magic.
Yes, this quantum magic, essentially. So the percentage, the probability that it decays one way or another is called a branching ratio. And these things are all being fleshed out, essentially. It's all about data. You can't know how often it decays one way without counting how often it decays not only that way, but every way. You can roll a dice, you can count the number of 3s on that dice. And you roll 10 times, you roll 3 3s. You say you have a 30% chance of getting a 3 then. That's the branching ratio, 3s on a dice, on a die. But you have to be able to do the counting. You have to have enough statistics.
So
that's certainly being fleshed
what
out.
kind of papers on properties do we expect the next year or two?
There's been a few out already, but as the next run of the LHC is starting, it should start in the next month. We ran last year, so we started, the LHC started, it was at, first couple of years it was 7 TeV and 8 TeV. Last year it ramped up to 13 TeV, and all this tells you is a higher energy, right, more massive particles. And so we're starting it again this year after the winter break at 13 TeV, and we're going to start really taking a lot of data. So we should have at least triple the data set this year that we did last year. And as soon as we get a big enough set, every 3 months or something like that, there'll be new information coming out in the forms of papers and what we call public information. So you should definitely check the Atlas website. There's all listed there. But there's already been a few out, especially on the spin and the branching ratios.
But nothing out of the normal?
Nothing so far. It's pretty much as predicted, which is boring. We don't want as predicted. We want something crazy, because then we have to it's something new and exciting. Something that's theorized and you find it exactly where you want, that's okay. The theorists get a Nobel Prize for that. We want to find something exotic and new. And things like supersymmetry, things that can really combine these grand unified theories, that can combine all the forces together in a unified way, in a very coherent way. This is really the next step. Because what we want to find is things that supersymmetry may predict some new particle, and we find it. We say, oh, great, now it looks like supersymmetry is the next new thing. But we don't know. This is the kind of transition period we're in. For years, we knew the Higgs boson, well, something like the Higgs boson must exist. We were searching for it. Now we found it. And now there's not really a next thing on the horizon. It's not like we're searching for that one new thing that we know must be there. Now it's an unknown. We know there has to be more because there's lots of unanswered questions, but there's not like one thing that we can go to the government and say, I want a new collider to find that. That's